So let's meet the members of the particle zoo. Now these are not all the particles that there are. There's really, literally dozens and dozens of known subatomic particles. Okay, these are just the ones that we need to think about when we talk about the fusion that happens in the sun that produces the energy that helps us all live. Okay, and so the first three are going to be familiar, and the last three are not. So let's meet the members of the particle zoo. Number one, the proton. Symbol P+. It's positive, right? It's also quite massive. Okay, let me do that. Proton, it is. Now, it's not massive, compared to, an elephant or even a mouse. But on the subatomic scale, it's an 800-pound gorilla. Okay. On the really the subnuclear scale, on the super tiny scale we're talking about, the proton is a large particle. It's quite massive. And of course it's positively charged. Okay. Number two is the neutron. Its symbol is just a plain old N. It has approximately the same size as the proton, so it's also massive. I'm not going to give numbers. I'm just going to let you know that it's a jumbo particle. Okay. So we got our positive proton. Over here, I'll put the charge. Okay. The charge of the proton is positive. The charge of the neutron is 0. No charge at all. The third one we're also familiar with, the electron. E minus. The minus, of course, indicates that it's negatively charged. Okay, so the charge there is negative. It is light. Okay, the mass of a proton or a neutron is approximately 2,000 times the mass of an electron. Okay, so it really is like comparing a 400-pound gorilla to a mouse. Okay, so if the proton and neutrons are 400-pound gorillas, the electrons are mice. They're super small when measured up against the protons and neutrons. Okay, so remember that they're very small and they're negatively charged. Okay, so those are all familiar. Okay, so those are all familiar particles. You have heard of these particles somewhere at some point in your life. The next three you may or may not have heard of, but they all play important roles inside the sun. The fourth one is known as a positron. It's given the symbol E+. It is also light. In fact, it has the same mass as the electron. Exactly the same mass. And as you can see from the name, it is positive. Okay. The positron, have you heard of antimatter? Well, it turns out antimatter is not just something you read about or hear about in Star Trek. Okay. Antimatter is a real thing. Antimatter exists everywhere. In fact, in small quantities, it's being created and destroyed all around us all the time. But in a practical sense, it does not last long. What happens when a positron and an electron meet? These are each other's antiparticle. The positron is the antiparticle of the electron. When they meet, we'll talk about what happens in just a second. Okay, but when they meet, something very interesting happens when a particle and its antiparticle meet. There are also things called protons, antiprotons, neutrons, antineutrons, and so forth and so on. The positron is basically an anti-electron. It's antimatter. And when these two meet again in just a moment, we'll say what happens. Okay, but the positron is just exactly like an electron. All the properties are just like an electron, but it is positively charged. So they have the same mass. They're both little mice compared to the 400-pound gorillas of the protons and neutrons. The fifth particle that's important to us is the neutrino. These probably are my favorites. Neutrinos are indicated by the Greek letter nu, which is like a little V with a little flag on the end of it. Okay. These are very light. These are far lighter than electrons. So if an electron and a positron are like mice, the neutrino might be something like a fly. Okay. Much less massive than the electrons and positrons. So we've got our 400-pound gorillas here, we've got our mice here, and we've got our, really like a gnat almost, like little gnats are the neutrinos. You can tell by the name, they are neutral. They have no charge at all. Zero charge. They're small neutral particles called neutrinos. Okay. And number 6 is gamma ray. And it's given, not too surprisingly, by the Greek letter gamma. This is also neutral and it is massless. Okay. Now a couple things to say about gamma rays. I've said it before, but I want to emphasize it again. A gamma ray is just light. Okay. It's just light that we can't see. The only thing that makes it different, the only thing that essentially makes it different is that it has a shorter wavelength than what we can see. If the waves, the light waves that we can see with our eyes are like waves on the ocean, like long waves, like maybe 20 feet long waves on the ocean. You see just think of the waves coming in at the beach. These waves are maybe 20 feet between them, 20, 30 feet between each wave crest, right? They're rolling in. They have so-called wavelengths of about 20 feet. So if I freeze frame them, the waves coming in at the beach, right, it's 20 feet between each successive crest. They're all moving towards me, but if I froze it and then measured the distance between the waves, maybe 20 feet between them. That's like the waves that we can see. Whereas gamma rays are little bitty short waves you might make in a puddle, on a little tide pool on the edge of the ocean. You get in the tide pool and you splash around and make those little bitty waves. That's gamma rays. Okay. So notice that the waves on the ocean, with 20 feet between them, and the waves in your little tide pool are the same thing. They're both water waves, right? But one of them is a short wavelength and a tiny little wave. The other one is a long wavelength. The long wavelength is the light we can see. The tiny little short waves are the gamma rays. So they're both the same thing. They're just different sides. One has a long wave, the other one's got a short wave. That's it. And our eyes cannot see gamma rays, and also gamma rays are damaging to us. In fact, gamma rays are coming out of the walls of your house all the time. But there's such a low level of them that they don't hurt us. Okay. If we increase that number a lot, it would begin to damage us quite a lot. In fact, when an atomic bomb is dropped, you heard of radiation sickness? That's produced almost entirely by gamma rays. Those are just high levels. That's billions and billions of times higher than the normal background level of radiation that we get all the time. There are some gamma rays floating around your house, coming up from the Earth. There's radioactive uranium down there producing gamma rays. There's potassium in your walls that creates gamma rays. But it's such a tiny amount it doesn't hurt us. Okay, if we amp that level up a lot, like dropping an atomic bomb, it would make us sick. So gamma rays in large doses are very bad for us. Okay, but it's just light. It's just light. And it is, importantly, massless. Okay. Now what happens when a particle like an electron meets its antiparticle like a positron is both the electron and positron, which have mass, disappear from the planet. They disappear from the universe. If you have an electron, oops, that's not an electron, that's a positron. if you have an electron meet up with a positron, you get gamma rays. You get, which is light, or energy. Remember the mass energy equivalence. We have lost mass. These two particles no longer exist anywhere in the cosmos, but now there's light that exists. We've taken the water in our mass bucket, right, and poured it into our energy bucket. Okay. Now this gamma ray energy eventually becomes the light that we can see. We look out at the sun. I'm looking out the window right now. The light I'm seeing out there originated as gamma rays in the sun's core. By the time it gets down to us, it's no longer gamma rays and no longer harmful. Actually, by the time it makes it out of the sun, most of it is no longer gamma rays. But this is energy. Okay. One more thing I want to say before this video is over. I quickly want to remind you of the four fundamental forces. So we've got gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force. Different particles experience different forces. Turns out that of these 6 particles, all of them experience gravity. But gravity is very weak and will not come into play when we talk about fusion. Okay, it's not important for the formation of energy in the sun's core. Okay, so all of them experience gravity. Even light, which is massless, experiences gravity. Electromagnetic force, all charged particles. So we have 1, 3, and 4 experience the electromagnetic force. The neutrinos do not, the neutrons do not, the gamma rays do not, because they are not electrically charged. Only the ones that are charged experience the electromagnetic force. Of these 6 particles, only the electrons, I'm sorry, I'm getting ahead of myself. The strong nuclear force, only 2 of these experience the strong nuclear force, and that is 1 and 2. Only protons and neutrons experience the strong nuclear force of the particles that I've written here. In other words, positrons, electrons, the force is right there, but they don't experience it. Okay? Just like a neutral particle does not experience the electric force because it's not charged, 1 and 2 do not experience the strong nuclear force. The weak nuclear force is experienced by the electrons. I'm sorry, I'm not going to put numbers here. By electrons, positrons, and neutrinos. Electrons, positrons, 3, 4, 5. Experience the weak nuclear force. So different particles experience different forces. Okay. Now what we're going to do in the next lecture is talk about how nuclei hold together. Okay. It's really weird. It's super weird that nuclei hold together. And as we look at the next video, I want you to particularly remember this bit of business right there. The strong nuclear force. Okay?